Good afternoon again. Okay, let's start. Okay, for this week, the tutorial includes two problems. The first one, here we have a rod of length L and mass M lies on a smooth horizontal surface and is subjected to a force P at its end A as shown. Here we have a rod with length L. We have a force P which is exerted on this rod in vertical direction. The surface is smooth. It means there is no friction between the rod and the surface. Determine the location D of the point about which the rod begins to turn. It means that the point, for example, if we assume here, this is the point which this rod start to rotate about it, it means this point is a fixed point. The velocity of this point is 0. And we can assume that at this point there is a pin which this rod is rotating about this point. For example, if we call it C. So we can assume that this point C is a pin connection between the surface and the rod. So this rod will have a pure rotational motion due to this force P. At this moment, we can write the impulse momentum equation. If we assume that this is a coordinate system X and Y, okay, we assume that this is axis X and this is axis Y. So in this coordinate system, we can write the impulse momentum equation, and also we can write the angular momentum equation. So in X direction, since we will have, of course, here in this equation, we assume that this is axis X according to this equation, and this is Y. So in X direction, we have force P. Okay, so we will have mass times by the velocity. The initial velocity of the rod before this force P is applied to the rod, the velocity is 0 because it's initially at rest. So this term, or the initial momentum, is 0, as you can see here. We have plus the impulse equation. The impulse, there is a force in X direction, which is P times by T. So P times by T is equal to the final momentum, which is M times by VGX2. And VGX is the velocity of the mass center in X direction in the final position. So we call it MVGX. The next step, we can write the impulse momentum equation, this time in y direction, which is, in fact, here we assume that y direction is the horizontal direction. So we can write the velocity times by mass, which is the first momentum, plus the impulse, which there is no force in horizontal direction. So these two terms is 0, and this term is 0 because the rod is initially at rest. This term is 0 because there is no force in y direction, and it must be equal to mvgy, or the final velocity in horizontal direction, because we assume that y is horizontal direction. So this term must be equal to 0 again, because in the left hand side it's equal to 0. Mass times by the velocity is equal to 0. Mass is not 0, so the velocity of the mass center in horizontal direction is equal to 0. This is the impulse momentum equation in y direction. And finally, we can write the angular momentum equation, angular impulse momentum equation in hg1 is the initial angular momentum, which is equal to 0 because, again, because it's initially at rest. We have the impulse momentum about the mass center, which is equal to P times by, if we assume that this is the mass center, the distance between force P and the mass center is L divided by 2. Yes. So it will be equal to P times by L divided by 2 times by T, because we are integrating over the time. So it's equal to P T L divided by 2. It's equal to the angular uh, momentum in final position, which is equal to the mass moment of inertia times by angular velocity in final position. So we can substitute here. We can substitute and we will extract a relation between the PT and omega. And also we know from the first equation, we know that PT is equal to M times by VGX, and also PT times by L over 2, which is equal to IG omega. As I told you, when this rod is rotating about a fixed point like C, it means that the velocity of each point is equal to the distance from that point and point C, and times by angular velocity. Here, for example, that this is the point C. Is my voice clear now? Can you hear me? Is the voice clear? Sorry, I was disconnected. Is my audio clear now? Okay, sorry. So we can continue. So we obtain the the third equation from the angular momentum. So we continue from angular momentum. When you want to use the angular momentum impulse equation, we extract a relation between this force P and the angular velocity omega. As I told you, when we have a pin connection, when we have a rotation, we assume that, for example, this point C is the point that the rod start rotating about this point. So point C is a fixed point or is a pin connection. We can assume that this is a pin connection. So the velocity of each point is equal to the distance from that point times by the angular velocity. For example, the velocity of point A is equal to this length times by omega, and the velocity of the mass center, which is here, is equal to this length, okay, times by omega. So we can write that this VGX, the velocity of the mass center in X direction, which, as I told you, X is the very vertical coordinates. So we can write that this VGX as a function of omega. So we can assume that VGX is equal to L divided by, sorry, the Y times by omega, which Y is equal to this length, as I told you. This length, for example, if this is point C, this length is equal to Y. Okay, so Yx, Vgx is equal to Y times by omega. Okay, so we use this equation for Vg. We can substitute into the equation 1, which is Pt is equal to M times by Vgx. So instead of Vgx, we substitute Y times by omega, and then we can, here in this equation, we can substitute, instead of Pt, we substitute mvgx, and then we can simplify and calculate that Vgx is equal to L over 6 times by omega. Okay, so from this equation, we can solve and obtain the velocity in x direction or vertical direction and solve this equation for y, because vgx is equal to y times by omega. We can substitute here and solve this equation, because in both sides we have omega. The omega will be cancelled out and we can obtain that y is equal to L over 6. Okay. Any question? Is it clear? Is loudly clear? Yes, we use the impulse momentum equation first in horizontal direction and vertical direction. In vertical direction, we find this relation between the pt, p times by t, which t is the time, is equal to m times by vgx, the velocity of the mass center in x direction, which x is the vertical direction. The second equation is the impulse momentum in horizontal direction, which results in mvgy is equal to 0. It means that the velocity of the mass center in horizontal direction is 0. And the third equation is the angular impulse momentum. From the third equation, we have the initial angular momentum, which is 0 because the rod is initially at rest. We have angular impulse about the mass center. If we write the moment about this mass center, it's equal to p times by its length, which is d, and L divided by 2, p times by, because the distance between point A and the mass center, which at the center, is L divided by 2. So it's equal to p times by L divided by 2 times by t, which t is again the time. It's equal to the final angular momentum, and the final angular momentum is the mass moment of inertia about the mass center times by omega. So this is the third equation. This equation is the third equation, a relation between p, t, and omega. From the first equation here, we substitute that p times by t is equal to mvgx. So here, instead of p times by t, I substitute mvgx times by L over 2. It's equal to by ig times by omega, which ig is equal to 1 over 12 times by ml squared. This is the mass moment of inertia about the mass center. So from this equation, we can substitute vgx is equal to y times by omega, because as I told you, if we assume that this is the point, of course, this d is not uh, clear, because this d, in fact, is the position of point C, which point C is the point that this rod is rotating about that. So, in fact, if we assume that this is D, it's not very clear. So we can assume that this is point C. This point is the mass center, point G, okay? And we call this distance Y, okay? We calculate this y. When we are rotating about point C, the velocity of the point G, which is the mass center about point C, is equal to y times by omega, because we can assume that this rod, okay, assume that this is the rod, this is the point P, and this is a pin connection, okay? This is point C, and this rod is rotating with angular velocity omega. So the velocity of this point, which is G, the mass center, this velocity, we call it Vgx, which Vgx is equal to y times by omega. Okay, so here in this equation, I substitute here, sorry, This is the problem. Okay, VGX, I substitute y times by omega. So in this equation, when you substitute VGX is equal to y omega, here in this equation, we have one equation with one unknown y. So if you solve this equation for y, if you solve this equation, this one, we will have m times by y omega L over 2 is equal to 1 over 12 m L squared omega. The omega will be cancelled out from the both sides, and we will have y which is equal to L divided by 6. Okay, or you can solve this equation for VGX. VGX is equal to L over 6 times by omega, and we know that it's equal to y times by omega. So y is equal to L over 6. When we know that this length is equal to L over 6 and this length is L over 2 or half L, so the D, which is the total distance from point A, this is D, D is equal to L over 2 plus Y, which is L over 6. Clear? Got it? Okay. The next problem, we have a 4-kilogram disc. A is mounted on arm BC, which has a negligible mass. So in this structure, this arm, in fact, has a negligible mass, and we only consider this disc in our calculations. Determine the angular velocity of BC. Oh, sorry, I forgot here. If a torque of 5 times by exponential half t Newton meter, where t is in second, is applied to the arm at C, here we have this torque. Determine the angular velocity of BC in 2 seconds starting from rest. Solve the problem assuming that part A, the disk is set in a smooth bearing at B so that it moves with curvilinear translation. So in part A, when we assume that this disk is moving in a curvilinear translation, it means that we can assume that this is a particle because it's rotating. So as we can assume that it doesn't have any dimension, and in our calculation we can assume as a particle. So the mass moment of inertia of this disk about this axis z is equal to the mass times by length squared, okay, which length is 250. For part B, the disk is fixed to the shaft BC. It means that, for example, here we have a welded joint. So in this case, when this disk is rotating about axis z, at the same time it has a angular, when you write the angular momentum, we will have an angular momentum due to its mass center velocity, and also an angular momentum due to its rotation about axis z. And finally, at part C, the disk is given an initial freely spinning angular velocity of minus 80k radian per second, so prior to application of the torque. So we have 3 parts. In first part, we can write the angular impulse momentum equation. For the part A, as I told you, in the first one, the initial angular momentum is 0 because the initial angular velocity is 0. It's plus the angular momentum in the time from 0 to 2 seconds. It's equal to the final angular momentum. The final angular momentum is equal to mass times by the velocity times by the length of the arm, which here it's 250 millimeter or 0.25. And as I told you, you can consider it the disk as a particle. So we will have the integral of 5 exponential half t from 0 to 2 is equal to 4 times by VB times by 0.25. So we can solve this equation for VB, and the velocity of point B is equal to 17.18. It means after 2 seconds, the velocity of this point is this value. We want to obtain the angular velocity. This arm is rotating about point C. The angular velocity is equal to this length, 250 millimeter, times by omega is equal to the velocity of B. So omega is equal to velocity of B divided by its R. Okay, so at part A, it's equal to 17.18 divided by 0.25. Clear? Is it clear, the part A? Okay. For part B, no, VB is not at the same of omega. I told you, when this disk, assume that this disk is rotating about axis Z with angular velocity omega, we know that the velocity of the mass center for this point B is equal to 17 meter per second. So the angular velocity is equal to this velocity divided by R, because when this disk is rotating about axis Z, let me use this. For example, when this rotating by angular velocity omega, the velocity of this point is equal to, if we call it VB, is equal to this length R times by omega. Yes, VB is equal to R times by omega, which R is 250. And we want to obtain this omega. This is the unknown. We have the velocity of B from the angular impulse momentum. And also we know that R is equal to 250 millimeter. So omega is equal to VB divided by R. Here you can see this is the omega. VB, which is 17 divided by 0.25. Clear? For part B, this time the disk is fixed. So when you write again, the initial angular momentum is 0. You can see the impulse during 0 to 2 is the same. I mean, it's equal to the integral of 5 exponential half t dt from 0 to 2. So in the left hand side, if compared with the previous part, the left hand side is the same, but in the right hand side we have another term. In addition to 4 times by VB times by 0.25, we have the I omega, which I is the the mass moment of inertia for the disk about its mass center, and it's equal to half times by m times by r squared, because this time the disk has an angular velocity. When it's rotating, it's not we cannot consider it as a particle. This is a rigid body, and it has an angular momentum due to its mass moment of inertia. Okay, so this time we have this term. Again, we know that omega VB is equal to 0.25 times by omega. So we can substitute here, instead of VB, we can substitute 0.25 omega BC. And if we solve this equation, again, we can obtain omega BC, this time is equal to 66.8 radian per second. This is for part B. Any question? Is it clear so far? Any question? Is it clear? Okay. And for part C, this time for part C, we have the disk has an angular velocity of minus 80. So this time the initial angular momentum is not zero. It's equal to minus I omega. Again, I is the mass moment of inertia of the disk about its mass center. But this time we have a negative because it's in negative direction. In the right hand side, we have again the same term when you are writing the angular momentum. In the final position, it's equal to 4VB times by 0.25 minus, because it has an angular velocity in negative direction, it's equal to minus I omega. And again, I is the angular mass moment of inertia about the mass center, and omega is AT. So this time again we substitute VB is equal to 0.25 times by omega BC, and this term, the impulse, angular impulse, again calculated like the previous parts, and we can obtain that omega BC is equal to 68.7 radian per second. Okay, so this is the third case. Any question? Is all the are these all the parts clear? Part A, B, which is a rigid body, and part C, which we have an angular velocity of minus 80 radian per second. Any question? Okay, if you don't have any question, we can wrap up this session. Okay, thank you, and have a good weekend. Thank you.